Okay, so welcome back to this next video in which we are discussing palmitoylation of IP3 receptors. Okay, so we've now discussed the structure of an IP3 receptor, and we now want to discuss palmitoylation so that we are ready and equipped to discuss IP3 receptor palmitoylation. Okay, so we'll start off with a general discussion of palmitoylation. Okay, right. So, palmitoylation involves sticking palmitic acid molecules onto residues within proteins, okay? So, palmitic acid has another name, basically. Its newer name is hexadecanoic acid, okay? And although hexadecanoic acid is more of a mouthful than palmitic acid, it's a useful name because it tells you exactly what the structure of palmitic acid is. Okay, so this tells you that you're dealing with a 16-carbon, fully saturated carboxylic acid. Okay, so here is our carboxylic acid group, and then we need 16 carbons, so the carboxylic acid group will be linked to a methylene group, and you're going to have 14 methylene groups in this hexadecanoic acid. So let's draw one, put brackets around it, and then subscript it with a 14 to mean repeat this 14 times. So basically, I've drawn one, but you're meant to draw it out 14 times. That's what this bracketing, subscripting means, basically. It's a way of getting around having to draw out 14 separate methylene groups. And then finally, of the final methylene group, you'll then have a methyl group. And that takes us up to 16 carbons now. So we've got one in the carboxylic acid group, one in the methyl group, and 14 in the methylene groups in between. That takes us up to 16. So this is the structure of palmitic acid, or hexadecanoic acid. Now, it's not palmitic acid that you're actually going to directly add on to proteins. Instead, you're going to add on palmitoyl coenzyme A. So palmitoyl coenzyme A is the molecule that you're going to actually use to add on the palmitoyl groups onto your protein. Okay, so let me now show you the structure of palmitoyl coenzyme A. Now, CoA is short for coenzyme A, and this is the same molecule that you have in acetyl coenzyme A, which is so important in the respiratory reactions. Okay, right. Let's have a look at the structure of this. So we need to look at the structure of coenzyme A. Now we won't draw out the full structure of coenzyme A. Instead, it will suffice to draw a box around the letters coenzyme A there. And all we need to know is that it has a phyl group coming off it. Okay, so here, this is a phyl group. So whenever you have a sulfur atom linked to a hydrogen like so, that's known as a phyl group. Okay, and I would urge you to think of phyl groups as similar to alcohol groups. Sulfur, after all, is in the same group of the periodic table as oxygen, and if this was an oxygen here, you'd call that an alcohol group. And sulfur, as I say, is in the same group of the periodic table as oxygen, so this has very similar chemical properties to oxygen. So basically, one of these phyl groups has very similar chemical properties to alcohol groups. Now, basically what you can do is you can form ester links between carboxylic acid groups and phyl groups in a similar way as you would form an ester link between a carboxylic acid group and an alcohol group. It's called a slightly different name when you do it with a phyl group rather than an alcohol group, but effectively it's an ester link. So if we imagine for a moment that that is an oxygen rather than a sulfur atom, then what we could do is we could bind this carboxylic acid group to this alcohol group by taking the alcohol group off the carboxylic acid group, the hydrogen off the alcohol group here. Okay, combining those together to make water, and then binding the carbon atom of the carboxylic acid group to the sulfur atom of the phyl group, okay, or what we were imagining was an oxygen atom. And this, if it was an oxygen atom, would then be called an ester link. Because it is instead a sulfur atom that we're dealing with here, it is instead called a thioester link. So basically, palmitoyl coenzyme A is the name for palmitic acid once it's been linked by a thioester link to, that's fine. Thioester link to a thiol group, basically. Okay, so basically palmitoyl, the word palmitoyl refers to this group here. So palmitic acid referred to the entire carboxylic acid molecule, i.e. with that alcohol group there on it. Palmitoyl means the palmitic acid molecule with its alcohol group taken off it, and then this structure you add on to something else like this sulfur atom down here, and that's why it's called a palmitoyl group. Okay, so that's the logic in calling this palmitoyl coenzyme A, because you've got a palmitoyl group attached to coenzyme A. Right, so it's palmitoyl coenzyme A molecules that you're going to use to palmitoylate proteins. Now, the type of palmitoylation we're going to discuss is called S-palmitoylation. There is another form of palmitoylation known as N-palmitoylation, but it's far less common. Okay, so S-palmitoylation is the main way that you can palmitoylate proteins, and it's the way that the IP3 receptors are going to be palmitoylated. Okay, so S-palmitoylation involves adding palmitoyl groups, okay, so in green here, onto the thiol groups of cysteine residues. So it's a specific amino acid that you can add palmitoyl groups onto by S-palmitoylation, and this is cysteine residues. Okay, and even when you're doing N-palmitoylation, it's still a cysteine residue that you palmitoylate. Okay, so you can only add palmitoyl groups onto cysteine residues. So let me draw a cysteine residue here. So I'll draw it as though it's within the protein. That's what is meant by saying a cysteine residue rather than a cysteine amino acid. So here's the amino group, here's the alpha carbon, here's the carboxylic acid group, and both the amino group and the carboxylic acid group are linked by peptide links to the amino acid before this amino acid in the case of the amino group, and the amino acid after this amino acid in the case of the carboxylic acid group. Okay, and the R group of cysteine consists of a methylene group with a thiol group coming off it like so. Okay, now what you're going to do is basically you're going to transfer the palmitoyl group from the coenzyme A molecule onto the thiol group of the cysteine residue. So let's draw our palmitoyl coenzyme A here. So here's the CoA, and it's linked by an ester link, a thioester link, to our palmitoyl group here. So here are the 14 methylene groups. So there's one, we'll put the brackets around it, and then a 14 here, and then a methyl group here. Right, and what we're going to do is we're going to break this bond between the carbon and the sulfur atom here, and covalent bonds, remember, consists of 2 electrons, one from each of the 2 members of the bond. So this bond will have an electron from the carbon atom and an electron from the sulfur atom. For the basis of just understanding the reaction, imagine that we give the electron from the carbon atom back to the carbon atom, and the electron from the sulfur atom back to the sulfur atom. Of course, this is not how the electrons will actually move in this chemical reaction, but for an understanding purpose, it's fine. Okay, and then we'll cut this bond between this sulfur atom and this hydrogen atom, and again, imagine that one of the electrons goes back to the sulfur and one back to the hydrogen. What you're then going to do is bind this sulfur atom to this carbon atom, which you can do because this sulfur atom has a free electron and this carbon atom has a free electron. You will then bind this hydrogen atom to this sulfur atom here of the coenzyme A molecule, and thereby you will regenerate the coenzyme A just as it was originally with its intact thiol group. Okay, and then you will have a palmitoylated cysteine residue within the protein, and that is how you palmitoylate proteins. So if we've got our polypeptide here, you'll find a cysteine residue here, and you'll stick a palmitoyl group onto it, and S-palmitoylation involves sticking them onto the thiol group of the cysteine residue, basically. N-palmitoylation, which is the only other form of palmitoylation there is much less common, and that can only occur if the first amino acid in the polypeptide is a cysteine residue, okay? And therefore, this first cysteine residue has a free amino group that isn't involved in binding to the amino acid before it. And in that case, what you do is you add the palmitoyl group onto the amino group here rather than the sulfur atom, which is why it's called N-palmitoylation, because you're adding it onto the nitrogen atom rather than the sulfur atom. N-palmitoylation, as I say, is far rarer, okay, and it's not going to be relevant to us when we're discussing about the IP3 receptor palmitoylation. So in IP3 receptors, it's going to be cysteine atoms in the middle of the polypeptide, and we're going to be adding the palmitoyl groups onto the thiol group of those cysteine residues rather than the amino group. Okay, right, and we'll continue this discussion in the next video.